format. But regardless of that, I'm just happy that we are able to gather a whole bunch of students and all attend this talk that I'll give on grid forming control for low inertia power systems. So before I get started, I just want to make sure that my screen is coming through okay and my voice is coming through okay. Can you all hear me?
Yes.
Okay, sounds good.
Perfect. It's perfect.
All right, perfect. So so let's get going. I want to start by just paying a little bit of acknowledgement to the people who actually did the work and funded the research. Most of the work that you will see today was done by my grad student, Mohit Sinha, while he was at the University of Minnesota. He has since graduated and he works in the private sector now. A shout out to collaborators who have made a lot of the analysis and experiments in this work possible. Florian Dhople at ETH in Zurich, Brian Johnson, who's at the University of Washington in Seattle, and Jason Poon, who's at Stanford. And funding acknowledgements to the National Science Foundation and Department of Energy for helping us do this to do this research. What I'm going to talk about today is going to all be based on this fundamental building block, which I'm preaching to the choir here. No need to introduce you to this building block of an inverter, voltage source inverter here, shown to be fed by a PV resource, could be other resources in practice. And I have a bunch of switches, in this case arranged in an H-bridge configuration, a filter connecting me out to a load, or it could be a grid or a network. And I'm going to make some measurements, in this case shown to be currents, it could be voltages at that point of coupling, process that through a microcontroller, which is going to implement my control code, and then close the loop with a pulse width modulation switching scheme. And all that I'm going to talk about today is going to be intelligence that lies within this microcontroller, right? So I'm going to talk about control strategies that can be implemented in order to give you some desirable properties from system as well as individual inverter level points of view, and we'll see what that's all about. And of course, I'm not going to talk about just individual inverters. As the name suggests, we are going to take these and we're going to drop them in a network. The network that we'll look at is going to implicitly have some a collection of heterogeneous DC energy resources, perhaps not all of the same rating and the same capacities. And these are all going to be interfaced with these power converters, with these inverters, with the capability of having this high bandwidth digital control, as we talked about. And when you stare at a system of this sort, where there is predominantly, semiconductor-based switching devices that are in charge of your energy conversion, a natural question to ask is, what really are the system-level challenges, right? From a big picture point of view, what do I have to address? What are the challenges in order to overcome to realize AC waveforms at the terminals of this and satisfy load requirements? And really, in a system of this sort, the first thing that comes to mind is variability. There's a lot of volatility in terms of, both uncertainties coming in from the source side. So you might have PV resources, for instance, that are subject to irradiance fluctuations. You might have loads that are, rapidly changing and so on. So there's a lot of volatility going on. And notice that there really aren't big generators that I'm relying on in order to help me stabilize waveforms, right? So that gets you an added challenge that you have to deal with. And then I also want to operate such a system with minimal communication. And I want to do this in a plug and play fashion so that I can drag and drop resources and pull them out without having to go through a fairly extensive validation process or having a very extensive communication network, at least for the bare purpose of primary control. And I'm trying to do this all within the constraints of not having much mechanical inertia. In fact, for the purpose of this talk, we'll assume that there's no inertia, right? So we'll assume that there's no stiff grid. Essentially, we're looking at networks where we only have inverter-based resources. So these are really microgrids in the true sense of the word. All right. So what is the state of the art, right? So the people have done this. This is what I'm going to talk about today. Is it does build on a wide body of research. And the state of the art method that has been proposed and is very popular in the literature is this method called droop control. And droop control was first proposed back in 93. There's a paper by Chandorkar Diwan in 93, and it talks about how to do this. And really the inspiration that they got here was to look at synchronous machines, right? And they said, hey, look, synchronous machines, when you run them in parallel, they work, right? They can support loads. So why don't we just take that operation and try to mimic that in some sense over on inverter-based generation. So what it does then is it looks at power converters, and it looks at the terminal behavior of power converters, and it imposes linear trade-offs. Now, the trade-offs that I've shown here may not be the only ones that are possible. I'm showing you here a trade-off between voltage magnitude and real power frequency and reactive power, which is something that you might want to do in slightly resistive dominant networks. In inductive networks, you might want to switch those. But the idea is we take these we take these notions of real power and reactive power, and we trade off voltage and frequency, and that basically gives you synchronization in complex networks. Now, there are a few limitations with droop control, and that's basically what I'm going to try and address with the method that I talk about today. The first the first and foremost limitation is that you are assuming sinusoidal steady state operation even before setting it, right? Anytime I refer to terms such as frequency, anytime I refer to terms such as average real power or average reactive power, I'm already assuming that I have sinusoidal waveforms that exist, right? And somehow I'm also trying to generate them at the same time, right? So you see this chicken and egg sort of dilemma come through. And anytime I'm dealing with phasor type quantities, I have to compute them. And so that automatically requires a few cycles of effort. It automatically requires averaging, and it kind of tends to slow you down. And then there's also this natural tendency to, once you have droop control, to build on it in a very hierarchical fashion, right? So as a result of all of these, we have hierarchies that are imposed in a slightly artificial manner. And the bottom line is that this ends up being quite sluggish. If you want to implement it in real time, if you want to implement it in really volatile settings, it'll turn out that that you are constrained by the definitions that you are using in order to realize it. And most of these definitions are quasi-steady state notions, which number one, may not even be valid in low inertia and high volatile settings. And number two, if you want to live with them, you are going to be faced with some time bottlenecks. All right. So what is our alternative that I'll highlight instead? And it's a time domain alternative, right? So there's a lot sort of illustrated on this particular slide, but I'll just draw your attention to a few key aspects, and that's what's essentially boxed in this blue box, and that's code that lives in a microcontroller that's providing you with your PWM switching waveforms. And the idea is that we are going to extract the sensed current from my inverter terminal. So this is a physical current that I'm sensing from the terminals of the inverter. And I'm going to extract it from a circuit that takes this particular parallel form, right? And this circuit has a parallel connection of a resistance and inductance and a capacitance. And we'll talk about tuning these parameters in a few slides to come. There's also a nonlinear element here, this function g of v, and this gain sigma, which I'll call your attention to. It's in fact one of the few parameters that I'll refer to over and over again during this talk. And this nonlinear voltage dependent current source, we'll see, gives us some interesting dynamic behavior. And the combination of all of this, is essentially an oscillator. Okay, so we'll see that this allows you to realize sinusoidal oscillations. And so we call this method virtual oscillator control. And it's virtual because this is all implemented in terms of ones and zeros on a microcontroller. So I take the dynamics of this oscillator, I discretize them, and I implement them. And the way I close the loop then is I extract the same current that I would, a scaled version of it, from this particular oscillator. And that's this current that's shown on the right here. And one of the voltage waveforms that is generated across this oscillator, and that's the capacitor voltage, is going to be sinusoidal in nature, and I can process that in order to realize my my PWM switching a modulation signal in order to get my my switching signals at the end of the day. All right, so that's how I realize it, and that's how I close the loop, and that's how I control my particular inverter. And you may look at this and you may say, hey, look, this is really strange, right? Like, why would I even try to do things this way? And we'll see that there are very well-defined reasons in order to rely on a method of this sort in practice. The one thing that I want to draw your attention to before we go ahead is that this is entirely implemented in real time, right? So there's no notion here of frequency. There's no notion of average power, reactive power, no additional computations that are that I'm hiding from you beyond what you see are the physical or the dynamics of this oscillator circuit all by itself. So that real-time aspect of this we'll see is going to give us tremendous opportunities for improving performance, especially over phasor domain-based methods. All right, so there's some compelling reasons to pursuing control methods of this sort, and I'll make those arguments from both the points of view of an individual inverter that's realizing a control scheme of this sort, as well as what happens when you have a collection of these all connected in a complex network, right? So I'll break up the next part of this talk looking at the individual inverter level performance, as well as then switching over to the system level. So let's take a peek at what happens at the individual inverter level when I pursue a method of this sort. All right, so in order to do that, it might be just useful to revisit what exactly this oscillator is doing, and some elements of this oscillator circuit might be reminiscent of other such dynamics that you might have seen in the past. And the fundamental kernel here is in fact this resonant LC tank, right? So this is a very simple second order circuit, probably serves as a template for introducing dynamics in calculus courses and so on. So you've probably seen this in many different contexts. So you have an inductor and a capacitor, and what you can do is if you tune the L and the C, right, to a frequency of your choice. Now over here, you don't have any control over the amplitude of the oscillations, but regardless of what initial conditions you have, at that particular initial condition, you'll always get oscillations here that are at frequency of 1 over square root LC. Okay, so this is a very classical circuit. We don't really need to get into too many details here, but I'm going to show you a sequence of waveforms in the slides to come. And in each case, I'm going to plot the capacitor voltage, and I'm going to project that over to the phase plane where I look at the inductor current and the capacitor voltage as well. So in this case, perfectly sinusoidal, I trace out an ideal circle over on the phase plane. Now, what happens if I stick a resistor at the end of this parallel connection? So in this case, if you write down the dynamics and you can work this out, you will see that you're always going to damp out oscillations, right? So no matter what your initial conditions are, remember in this case, everything is unforced, right? No matter what your initial conditions are, they're always going to damp out to zero. And the behavior here, let's say for the capacitor voltage, is going to look like this. It's oscillatory, it goes out to zero, and then projected out onto the phase plane, we get the spiral that decays to zero as well. Now, again, these two cases are interesting, but they're not really what we are after. Okay, so what we're after is we want to have controlled oscillations at amplitudes and frequencies that we can regulate. And so one way of doing that is using this particular oscillator structure that I talked about earlier. And this type of oscillator, we call it as the dead zone oscillator. So not only do I start with my fundamental kernel of my inductor and capacitor connected in parallel, I use a resistive element, and then I stick this nonlinear voltage-dependent current source here at the ends of this linear circuit as well. And what this unit is now going to do is it's going to yield self-sustaining oscillations. The frequency of these oscillations is still going to be given by the resonant LC tank. And then I have a bunch of other parameters that I can play with in order to set the amplitude. In this case, it's going to be the slope of this nonlinear voltage-dependent piecewise, or I guess piecewise linear voltage-dependent current source sigma, this breakpoint var phi, as well as the value of this resistance, right? So the combination of these three terms, it turns out, is going to allow me to set the amplitude. I won't get into exactly what that precise one-to-one relationship is, but the fundamental idea is the LC tank sets the frequency, and then a bunch of these other parameters can be tuned in order to set the amplitude. All right. So what do you do when, or what do you get when you look at the waveforms that are generated by this particular oscillator? Now it turns out that no matter where you start in the state space, right, whether you're starting within this this green circle, which is essentially the closed form sinusoidal steady state solution, or you're starting outside of it, right? So no matter what your initial conditions are, you're always going to get to that sinusoidal steady state solution asymptotically. right? And this is actually going to be exponentially stable. So that's great. I can tune the amplitude, I can tune the frequency, and now I don't have to rely on just initial conditions. It is controlled in a very well-defined sense, and it's going to be stable as well. Right. So the one thing I want to mention is how does this all sort of relate to droop control? And the idea here is that what I've shown you is something that exists outside of just sinusoidal steady state operation, right? So if you just think about this and in a slightly more abstract fashion, you will quickly realize that droop control is only acting on the sinusoidal steady state. Whereas, and its operation, in fact, outside of the sinusoidal steady state is not even defined. You don't know what it even means to be outside of the sinusoidal steady state if you let your droop equations go. But this idea of this virtual oscillator control, this time domain method, you can start at any point in the state space and you'll always regulate it back to the sinusoidal steady state. So close to sinusoidal steady state operation, it resembles droop, but outside of it, the dynamics are still well defined, and you can show that you'll get to this desired state in at least asymptotically. And we've run experiments and we've characterized the steady state behavior of this nonlinear method. Here's a quick set of experimental results where, again, the oscillator was tuned to give you linear trade-off or close to linear trade-off between voltage and real power, frequency and reactive power. And what's shown here are experimental results from a particular realization and analytical curves that were generated by looking at the dynamics of these oscillators in steady state. And you can see that even though there's a lot of nonlinear dynamics that I'm relying on in order to generate my PWM waveforms and close the loop and do all of that closed loop control, in steady state, I still get close to linear. Okay, so this is not exactly linear, but it's close to linear trade-offs between voltage and real power, frequency and reactive power. And I can interchange those through some clever manipulations in the controls as well. But the fact is that in sinusoidal steady state, I can characterize its behavior, and it does boil down to something that is droop-like. And that's great. All right. So as I said, part of this is going to be something about benefits that you get at the level of an individual inverter. And then part of it is going to now focus more at the system level. So I hope at least to some extent, the benefits at the individual inverter level are well defined in the sense that it's a real-time control method. I'm able to generate sinusoidal waveforms, prove that they are stable, and I don't have to constrain myself to living within this universe of phasors and quasi-steady state constructs. All right, so switching gears, what happens when I now look at system level behavior, right? When I have a collection of these inverters, all of them implementing this particular control strategy. So why would I even do something like this, right? So there's a well-defined reason. There's some method to this madness, and the inspiration is really from nature, and it's from nonlinear dynamics that are observed in many different natural phenomena as well as engineered phenomena. Over here, I'm just showing you some examples that naturally pop out of nature. So you have schools of fish, you have fireflies synchronizing in unison, you have birds flying in formation. In many of these observed phenomena, the idea or the fundamental notion is the same, and that is that you have a single agent which by itself and on its own accord has the capability to execute some fairly complex nonlinear dynamics. Right? If you think about a bird, if you think about a fish, a firefly, you know, this is a very complex organism. It's a very complex physical being, and it's capable of executing some fairly complex behaviors. And the idea is when you couple them through a network, you have emergent group behavior that if you do engineer correctly, so this was perfectly, these were examples that are coming very naturally, but if you think about an engineered system where you try to replicate the same idea, you can definitely start to now engineer group behavior and group dynamics that are, number one, emergent, and number two, suiting your desired application. So that's the fundamental idea that we are tracing out. And in the physical or you know, engineered systems, this has been observed for a very long time. So for instance, one of the earliest observations that was made was by this Dutch scientist Christian Huygens, and in a letter to the Royal Society of London way back in 1665, there was a remark that was made following an experiment where two pendulum clocks were noted to synchronize by merely being connected over a wooden plank. And Christian Huygens himself was was very surprised by this. He thought initially that it was air flows that were causing them to synchronize, and only later on was it realized that it was no, it was the mechanical interconnection through this plank that was causing these pendula to synchronize, and he called it an odd kind of sympathy. Which is quite poetic in some sense. So this has been observed for a very long period of time. It's just that we are now utilizing this in engineered systems in order to get us emergent behavior without any communication beyond what might exist in that engineered network by itself. So let's go back then and see what happens when I connect all of these units in a particular network. So I'll take you back to this realization of this virtual oscillator. Again, remember, we are just taking the dynamics of this. It's a second order system. There's some nonlinear elements, but I can eventually discretize all of that using my favorite discretization rule, realize it as ones and zeros, programming it on a microcontroller, and close the loop in the fashion that I described earlier. And I again want to draw your attention to one quantity which we will talk about and reference quite frequently, and that's this gain sigma. Okay, so just keep that in mind. It's just this slope of this nonlinear function that I have in this particular oscillator. All right, so what I'm going to do is we've looked at this and we've characterized network behavior in fairly complex settings, but I'll present a result which I thought was very intriguing, and this is coming from some of our early investigations in this area, and that was the most simple, symmetric, uniform network that you can build, a collection of these inverters connected in parallel across a particular load. And I'm not going to impose any characteristics on the load. And what we have here is a collection of these inverters, all of them controlled with this virtual oscillator control, and there's no communication between any of these inverters. And the impedance at the output of the inverters I'm capturing by this quantity Z net. These currents that I provide to the load are denoted by IO1 through ION. And what I'm interested in order to synchronize and provide power to the load here are to perfectly synchronize the waveforms VO1 through VON. So it so turns out that using the equivalent circuit representation of my oscillators and recognizing that I can average away some of the fast switching behavior, what I can do is I can represent all of these inverters with these circuits, right? In a time scale where I'm only interested in AC cycle waveforms. And so now you see this RLC circuit coming through. You see this nonlinear voltage dependent current source, this function G coming through, and then the rest of the network remains the same. And it so turns out that we have a condition for global asymptotic synchronization in this particular parallel setting. And what this means is that asymptotically, all pairwise differences of all voltages are going to go to zero, circulating currents between inverters are going to go to zero, and I'm going to realize a sinusoidal waveform that's perfectly synchronized at the load terminal. All right, so let's take a look at what exactly this condition for global asymptotic synchronization is in this particular setup. Now, this is what it says. So there's a few terms that are involved here, and again, we won't get into all the details, but I'll just draw your attention to what are the three key terms that we have here. So we have the impedance of the network. Okay, so that's this term Z net, and that's I'm assuming everything is universally symmetric and all impedances are uniform to set a baseline characterization here. And then we have this oscillator impedance. So this is just the RLC impedance for my individual oscillator, and you will immediately recognize that this is the parallel connection of these two impedances that shows up. It's the equivalent impedance that comes about from the parallel interconnection, and I'm looking at the maximum value of that across all frequencies. It's the product of that and the gain that I had for this nonlinear term, for this nonlinear voltage dependent current source. So what this is saying is, as long as I have the product of these two terms to be less than 1, I'm going to have a guarantee on global asymptotic synchronization of the waveforms at the terminals of my inverter. Now, if you just, we'll take a quick look at how this is derived. But if you just stare at this, we'll see some very interesting properties that come out of this from a system point of view, right? So I'll claim that this condition tells me that this control method is 3 things. It's modular, it's robust, and it's resilient. And I use these terms with specificity. And what I mean by that, why do I call it modular? Well, the first thing you'll see here is that there's no nowhere that capital N or the number of inverters shows up, right, in this particular condition. What that tells me is I can add inverters in and out. I might have 2 inverters or 100 inverters. The condition for this synchronization, the condition for synchronization remains the same. So it does give me that plug and play nature, and it does guarantee modularity in terms of realizing this particular microgrid. The second thing I'll note is that it's robust. And again, I use this term in a very specific manner. Why do I call it robust? And that's entirely because the load does not show up anywhere in this condition for synchronization, right? So the load could be linear, nonlinear, and it could exhibit quite complex behaviors in its own right. And we'll see that in some of the experiments that I outline in forthcoming slides. But again, the load does not show up. And so it is robust to what's happening on the load side. And then I'll also mention that it's resilient, because in order to get this fairly strong condition, I'm again able to realize this with no communication beyond what I'm having implicitly or inherently via the electrical interconnection of these inverters. So the only thing I'm leveraging here is the electrical interconnection in order to get me this condition for synchronization. All right, so I'll give you a very quick sketch of the proof for those of you who might be theoretically inclined or just intrigued. And the idea here is that the first thing that you might think of doing is to, construct a storage function or a Lyapunov function that might be proportional to signal differences. And that does work, but it works very well given the parameters that I have specified for resistive networks. But it so just turns out that in the network that I'm looking at, I have energy storage elements that are coming in as a result of the inductive lines. The loads might have energy storage components and so on. So it just so turns out that in this complex setting, it's quite challenging to set up a Lyapunov function that has all the properties which would allow me to conclude that I'm going to get global asymptotic synchronization, right? So we're not going to do a Lyapunov-based analysis in order to show synchronization and in order to show these desirable properties. What we'll do is we'll leverage an L2-based method, and this is really looking at a product of 2 gains of these systems. There are 2 types of systems here. There is a linear collection of all the, let's say, the oscillator linear components as well as the network linear components, and I'm sort of combining all of that, and I'm calling it a giant transfer function matrix. This function f, and then there's a bunch of nonlinear elements that I'm collecting in the feedback path, right? So the approach that we follow is to compartmentalize the subsystems, a bunch of linear things in feedback and a bunch of linear, in the feed forward path, a bunch of nonlinear terms in the feedback path. And then what we do is we do a simple coordinate transformation using a projector matrix, and this matrix allows you to define a state space, which is a function only of state differences. And then in such a system, if you're able to prove stability, right, you get synchronization in the original set of coordinates. Okay, so just think about that, right? If you're able to prove stability in this system where everything is written in terms of signal differences, what that tells you is that in the original dynamical system, I'm going to get synchronization. And there is a loop gain that you have to trace out. And so as a result of tracing out this loop gain, you naturally get that there is a gain associated with the linear part of your system and a gain associated with the nonlinear part of your system. And so the linear part of the system manifests the gain in the terms of this parallel connection of these impedances and the maximum value of that across all frequencies. And then the nonlinear part of that system, remember this was this piecewise nonlinear current source, and that comes across as this the slope of that current source, and that's where you get the blue part of this, or the sigma. So the product of these 2 gains is less than 1. You will get stability in this coordinate transformed system where I'm looking at signal differences, and then that maps to synchronization in the original system. So that's about as much detail as I'll provide about how we prove stability. There's a lot of technical details here, which I'll direct you to the papers for more information. All right, so the next thing I'll do is I'll just say is just a little bit about research philosophy, and I want to point out that whenever you think about validating an idea, it really has to go through an entire cycle where it goes from pen and paper to modeling and simulation, and then you really have to think about experimental validation, especially for concepts of this sort, right? So I'll kind of show you some experimental validation, which really allows us to have a lot of faith in some of the theory that I talked about. So here's the first set of experiments that I'll present. It's a set of three. This was really benchtop stuff. A set of three inverters connected through inductor filters to a set of many different loads, and we'll cycle through a few different loads to see the behavior of this particular control strategy. And each of these has their controllers that are implemented with using this virtual oscillator control method. There's no communication between individual inverters. And what I'm going to plot are a sequence of oscilloscope waveforms where I'll show you four things. In each of these, I will show you the currents, which are sketched or which are highlighted here in blue, in light blue, and in purple for these three inverters. And I'll also show you the load voltage waveforms that we were able to realize, which is shown here in green. All right, so let's just run through a few different types of experiments. So here's one of the very early ones that we did. It's a collection of these three inverters, as I said. One of them is smaller than the other two. Okay, so there's a third inverter here, IO3, which is the current coming from the third inverter, and this third inverter is rated to be 50% of the capacity of the other two. And I'm just going to switch in a load resistance in and out, as is shown here on the very right. And I'll also show you what happens at startup. Okay, so remember, again, there's no communication between these. I'm initializing them with random initial conditions. So in startup, which is the figure on or the oscilloscope capture on the top left, I'm seeing the load voltage build up. I'm seeing the currents, IO1, 2, and 3. They are initially, as I said, completely out of phase. They are doing a song and dance routine. And then without any communication, eventually they will synchronize. And you see here that IO3 is actually providing or is actually one half of the amplitude of IO1 and IO2, showing you that, with a little bit of engineering, and I didn't tell you exactly how you can engineer this to get you to that to get you to that required capacity, but there is tuning of the parameters that you can do. You can get this power sharing in a very nice way, right? And then the figure on the top right is showing you what happens as a result of a load step. So you see that there is a load step that's instituted, and in the middle of that particular waveform, all the currents increase in amplitude, and they still maintain power sharing as a result of even after going through this large signal transient with no communication. The load voltage remains rock solid, and we still maintain synchronized current waveforms getting out into the load. All right, so that's what you have. That's what you have at startup. That's what you have with, let's say, load steps. What happens if you have a nonlinear load, right? So I made a big deal about saying that, hey, look, the load characteristics don't really show up in the synchronization condition. We're able to see this in practice as well. So here's a collection of these three inverters that I'm going to have, and I'm going to connect them across a full bridge rectifier load. So the currents that are provided by these inverters now take this very familiar form that might be familiar to you for circuits of this sort. And I'm also going to do a large signal change here. At some point of time, I'm going to add and remove this third inverter. All right. So what you have here in the very beginning are the three output inverter currents, perfectly synchronized. They're going along nice and steady. You have the load voltage. I take out the third inverter. Immediately you see that the other two pick up the load, and the load voltage is unaffected as a result of this large signal transient. What happens if I throw in a third inverter? Well, you have two of them that are providing the load power. At this particular instant, I bring on the third inverter, and then I'm able to, you see the other two automatically kick back on their power production, and then I'm able to satisfy the load through this large signal transient. And really, the point I want to make here is that, hey, look, I had a very nonlinear load, and still things end up as desired and as engineered in order to get me my load voltage, in order to get me this dynamic performance, which is really quite fast. All right. What happens if you have RLC loads? Again, this is now just running through the motions here, but you can, provide a wide range of power factors and still get all of these desired behaviors of synchronization, of fast dynamic performance, and so on. So here's just a sample set of waveforms where I'm going between, capacitive loads to inductive loads and back, and still able to see all the desired properties and performance attributes as I did see from before. All right, so I did talk a little bit about, so that was the first set of experiments. I'm just going to switch to a second set of experiments here. And I talked about comparison with droop control. I showed you that if I at least have one individual inverter, I'm able to characterize its terminal behavior, and I get this sort of close to linear performance at its terminals. But there really are time domain benefits to be had outside of that. So I made a big deal about this control being a real-time control strategy, and now we'll sort of see what that really implies in terms of dynamic performance. So here's again a set of two experimental results that I'll provide. The template is similar to before. I have these three inverters connected in parallel across the load. I'll show you the three currents, I'll show you the load voltage, and I'll bring on a third inverter. And I'm going to do this for two different control strategies. I'll do this for droop control, a realization of droop control, and a realization of this virtual oscillator control. So on the left here are the results for droop control. So remember what I'm doing. I'm bringing on a third inverter, and the top waveform in the figure on the left is the load voltage. The ones at the bottom are the currents, and if you can measure sort of the time to synchronize this for the particular experimental setup that we had, and it was on the order of around 400 milliseconds, a few AC cycles. For the same terminal characteristics, right? So for the same terminal droop characteristics, if I run this oscillator type control, we can get close to an order of magnitude improvement in time domain performance. So they synchronize about 10 times faster, and with the same sort of steady state performance, right? So I can engineer the droop curves to be similar, but on faster time scales, I can really do a lot more with real-time control strategies, such as the one that I'm sketching out. All right, so I'll start wrapping up here, and I'm going to tell you about a few extensions that we have pursued with this particular control method. The first thing that might come to your mind is what happens to three-phase systems, right? There's again sort of neat engineering tricks and neat tricks from dynamical systems that you can play in order to get from the single-phase instances that I talked about earlier and start to realize three-phase controllers. And the way we realized three-phase controllers, at least in early incarnations of this control strategy, was to leverage the fact that, hey, you have this capacitor voltage, but you also have an inductor current, which is in fact 90 degrees out of phase from the capacitor voltage. So what you can do is you can take these two waveforms, you can run them through through a simple transformation, an alpha beta to ABC transformation. And then starting from waveforms that are 90 degrees apart, you can generate three-phase waveforms that you can then use to close the loop on a three-phase inverter, right? So these three-phase waveforms can then be utilized in your PWM switching scheme appropriately. Here's a very simple setup that kind of illustrates this. Again, adding on a little bit more functionality. I'm throwing in maximum power point tracking functionality by tuning a few parameters. There's many different ways that we have done this, and others have tried this in the literature, but just sort of showing you that you can extend this to now start looking at more complex networks, three-phase networks here, where you might have loads that are at the terminals of inverters. You might have non-negligible line impedances. You might have transformers, centralized loads that you have to supply, and one of them might be an MPPT-based three-phase inverter. And at least we're still able to show that you can realize MPPT functionality with a little bit more engineering on parameters and ride through small and large signal disturbances, even in this more complex three-phase setting. All right. The second thing that I'll talk about, and this is another very interesting extension, and that is the idea that this kernel that we have and the fundamental building block of all of these controllers were these nonlinear oscillator dynamics, right? And there's with a little switch, you can actually realize much more interesting behavior that might be useful in other contexts. So the idea is the same. You have power converters that are all connected in parallel. Now, I'm not going to tell you whether they are AC or DC waveforms, but you sort of see where I'm heading towards. I'm closing the loop with a gain. And this oscillator control is sort of what we talked about earlier. You can utilize many different types of oscillator dynamics as well. And it just so turns out that the sign of the feedback here is super important in terms of realizing one type of behavior or the other. So if I use negative feedback, I get synchronization of waveforms, and I can use that in order to synchronize waveforms in, let's say, AC settings, where I want to realize performance without circulating currents, build up load voltages, and so on. But it turns out that if I switch the sign of the feedback, so if I go from negative feedback to positive feedback, the waveforms that I generate from these oscillators are going to all go out of phase, and they're going to be perfectly phase balanced. And that I can use to actually interleave switching waveforms, let's say for multi-phase DC systems, right? So I'm not going to get into the details of this, but I'll just show you, what you can do, and I'll refer you to a paper if you're interested. And the idea here is the same thing. You have parallel converters, but now they are DC-DC converters. They're connected across a load. And the performance objective here is to interleave the currents that are being produced by the individual DC-DC converters so that the load current is flat. And I'm able to, get away with filters that are much smaller, increase power density, and get cost benefits along the way. Now, there's many different ways in which you can do this. The most common way that this is probably done in practice is a centralized controller, right? Where you have a central control and computing unit that's coordinating all the switching waveforms in a very precise manner. The state-of-the-art method is actually this is a distributed method where you might have a communication bus, where again this switching behavior is precisely timed out and then relayed out to the individual controllers. But really, in both of these, you have some level of centralization. You have some additional communication that's needed. This comes with cost and reliability bottlenecks. But if you use, again, this oscillator-based control, it's going to give you a completely decentralized solution. The communication that you need is inherently and implicitly just available as a result of the network. And by flipping the sign of that feedback, I'm able to get interleaved waveforms, right? So again, I'm not showing you the realization, I'm not showing you all the details or the analytical guarantees that we have for the setup. I'll point you to the paper, but just trying to pique your interest in this particular direction that, hey, you know what, the same sort of nonlinear dynamics can be leveraged in other settings in order to give you dynamic behavior that you might very least expect. So at least to the best of our knowledge, this was the first instance of decentralized switch interleaving that was proposed in the literature, and we did this back a few years back. All right. So in summary, what I've done is, and I'll again place the summary in the context of the AC system. So I presented a time domain control alternative, and really it's a control alternative to group control, which has really dominated interest in this space for a very long period of time. But contrary to group control, I'm able to implement these dynamics in a real-time sense, and that gives me several performance benefits. But in addition to performance benefits, I'm also able to get several theoretical guarantees on performance, right? And I'm able to get theoretical guarantees on dynamic performance, both at the inverter level, as well as the level of, as well as at a very broad system level. Okay, and that's something that you may not be able to get very easily with Droop. And I want to point out that, you know, in building out these controls, you have to really pay attention to dynamics that are relevant across domains. So we have looked at many ideas that come from circuit theory, some ideas that come from physics, from nonlinear dynamics, and these dynamics are even studied in fields such as systems biology and so on. So it really tells you that you have to look outside of your domain boundaries in order to take ideas from these different fields in order to realize solutions of this particular form. And lots of future work. I won't get through a laundry list here, but, you know, ideas of interoperability. How is this going to work with synchronous machines, with other types of grid forming controls? How can this be dispatched? How do I coordinate this perhaps at a higher system level to get me some more some more finer control for power optimization and so on. So these are all sort of, I wouldn't say future work, they're really part of our ongoing investigations. But there's really a lot that can be done to take such nonlinear controllers to the next level. So with that, I will pause, and I hope that gives us plenty of time for Q&A. Thank you so much.
Thank you, sir. That was a really influential talk. So, sir, I have a question, not question, it's a curiosity. Just like when we're inserting the PV, PV basically don't insert the inertia into the system, especially if we are inserting the PV and not backing up them with the energy storage system. So in that case, the inertia is reducing. So is there any limitation on based on the controllability of the system, how much PV we can insert?
I think that's a very broad sort of system level question. There are lots of limits that do come about. It depends on the type of loads that you might have. This idea of inertia, I just want to say that you have to take this with a little bit of caution, right? Because it comes from synchronous generator world, right? And if you think about an all-inverter system, even that idea of inertia doesn't really make it doesn't really hold that much water, right? But yes, will you run into sort of stability issues if you're facing with systems where you have upwards of 90% inverter-based generation and only a few loads that might be volatile in nature? Absolutely. But I think the broad solutions to that can never be obtained, because it's going to be case by case or system by system specific, if that makes sense.
Thank you, sir. So there are two more questions that came to me. So let me just read out to them. So the first question is there any mathematical restriction or the proof that decide why a droop characteristic is only restricted to the steady state sinusoidals?
So if you just look at the way droop control is, it just comes from the way it is realized. So the way you would realize it is you would when you're writing around the equations itself, you will say, okay, voltage magnitude is this function of real power, right? And it's not just real power, it's averaged over many cycles. And then let's say frequency is this function of real power or reactive power. So when you're writing down those equations, you have to realize that frequency in itself, right, or real power or reactive power, all of these concepts are only defined in the way that we know it for sinusoidal operation in steady state, right? So that's what I mean by the fact that for droop, there really isn't a good qualitative or quantitative description of time domain performance. If you're using phasors and you're willing to live in that universe, that's perfectly acceptable. You can always characterize its sort of quasi-steady state behavior very well. But if you want to write down differential equations and you want to know what happens on faster timescales, or you want to prove that, hey, look, you're going to get to these sinusoidal steady states, that's very difficult, if not impossible, to do with phasor domain methods such as droop. That's what I meant.
Thank you, sir. So there's one more question from Mr. Panda. He is asking while designing the control parameters for the hardware implementation, we have usually adjust what we calculated in a Bode plot approach for the simulation. So what parameters should be considered to bridge this gap?
Okay, so that's a good question, right? So how do you, I guess the broader question there is, how do you align this with classic control design methods where you might have used, let's say, Bode plots? Now, it becomes a bit challenging to use some of those methods since we have a lot of nonlinear elements. I'll point you to a few papers that you can maybe access through our website. And the type of methods that you use in order to characterize and in order to benchmark performance or to design parameters are all coming from nonlinear control systems theory. So for instance, there are ideas such as perturbation, there are ideas such as averaging, there's a bunch of tools that have been developed for nonlinear control systems that you can use in order to both characterize the performance of this type of architecture as well as tune parameters. But conventional methods to a degree are going to be limited, right? So if you think that you're going to get away by using Bode plots, for instance, in order to tune performance, in order to get a perfect idea of what's going on, you might have to do a little bit more than that, or maybe methods of that sort may not directly apply in such nonlinear controllers.
Thank you, sir. So there's one more question from Mr. Vineet. He's asking, in the case of a 3 lakh inverter having batteries on the DC side, won't unbalanced loading deteriorate the battery life, especially the tripling harmonic components?
Unbalanced loading deteriorate the battery life. I'm sure it does. I think this is maybe a little bit more of a sort of a hardcore power electronics type question. We haven't, gone into such type of power quality and very precise characterization of battery life and so on. But if you are, if you face issues of that sort in conventional settings, then yes, they will probably be faced in any three-phase setup. The solution that I proposed was not trying to address issues of that sort.
Okay. And there's one more question from Mr. Bandopant. He's asking, what are the challenges while implementing the proposed method for the inverter connected to a large network and operating along with existing synchronous machine? Maybe the stability challenges, hierarchical control, etc.
That's an excellent question. Okay, so there's lots of challenges, and many of them are faced in group control as well. So it's not any different from what you would face in a method such as Droop. I think over here, what you get is this added benefit of having the dynamics very precisely characterized. So you're never sort of left in the dark searching for, if you want to, let's say, just look at eigenvalues, okay, of a linearized system description. Well, it's quite easy to do with a setup of this sort. If you have to do it with Droop, you'll have to do a little bit of effort in order to get there. So what challenges you're talking about, whether they are stability challenges, control challenges that are more hierarchical level, everything that you have in Droop, you will face with this method as well. What this does give you, though, is a precise characterization of the time domain performance. So it does help you in terms of in anytime you're dealing with something in the time domain, such methods are going to be much more favorable from an analytical point of view. But from a system level, yes, we have the same interoperability challenges, the same stability challenges, the same hierarchical control strategies. How do you realize all of that? All of those things come along for the ride. But yes, that's a really good observation.
Sir, there are two more questions. So if your time is permitting, we will go with that. Otherwise, I can skip them.
No, I'm perfectly fine. I see we have 4 more minutes. It's Saturday night here, so I'm not doing anything exciting tomorrow.
I was worried because it's maybe 12:30 over there, so I was just worried about that thing.
Again, it's Saturday night, so in fact, I was planning on maybe sticking around for the next session as well. So I'm perfectly happy sticking around.
So I'll just directly come to the question. So the second last question is, what about the TSD levels? So with the nonlinear oscillator, is it lead to the bifurcation if not properly designed?
Okay, so now there's many different types of nonlinear circuits, and they all have very complex dynamics. The ones that I showed you that we are using, they belong to a class of systems called as Leonard systems, and they have very well-defined oscillatory behavior. In fact, there's lots of analytical guarantees on its performance. So you do get, in fact, much more guarantee that you will always get to sort of sinusoidal steady state operation. But yes, this is something you have to be aware of in nonlinear systems, right? So if you think that you can just throw any circuit at it or any nonlinear dynamics at it and you can hope for it to work, that might not be the best thing to do. So I want to point that whether it's this dead zone oscillator that I presented, there's a Vanderpool circuit, there's many other types that we have investigated. A lot of them fall in this category called as Leonard's oscillators, and those have very well-defined performance characteristics, which are very well suited to AC systems. As far as harmonics is concerned, this goes back to an earlier question, which was again excellent that we talked about, and that's about power quality and so on, right? Or what are the tools that I can use to design this? So there are methods called as perturbation methods, which you can use in order to characterize the harmonic content in the waveforms. And again, I'll point you to some of the papers that we have written on the topic, where you are able to, in fact, relate the parameters of your oscillator or your nonlinear dynamic circuit to, let's say, the amount of third harmonic content or fifth harmonic content and so on, right? So you have to do a little bit of effort in order to tease out those relationships, but you can quantify the performance in that spectrum as well. I think that answers both aspects of your question.
Thank you, sir. So last question of the session is from Mr. Siddhant. He's asking which microcontroller you have used, sir. Do you require a very high speed clock speed controller that for that, as normally the ADCs are multiplexed?
Again, good question. We have not used anything super fancy here. This was all TI digital signal controllers, and that was very well suited for the particular application. We didn't use any sort of FPGAs or anything more fancier than that. There are implementation issues, of course. There are few practical challenges that you will come across, as with any type of implementation of this sort. I can't think of any that are, that suggests that you need a very fancy microcontroller. So you can just get away with any sort of microcontroller that you're using for inverter control applications. The ones that we used were TI, mostly TI systems.
Thank you, sir. So I hope everyone has enjoyed this presentation. So thank you very much for answering all the questions and for a great presentation. Unfortunately, because of the time constraint, I wasn't been able to raise most of the questions from the audience. So maybe they can reach out to you if they have any further doubts and questions. They can mail you directly.
Absolutely. I would very much look forward to receiving further questions over email. Please feel free to reach out and I can point you to papers and look forward to any discussions that you might want to have offline. Thank you so much for giving me this opportunity, Gaurav. I really hope to make it out in person at a future event. But under the circumstances, I really appreciate you folks pulling together such a great program. Thank you so much.
Thank you, sir. So we just like to give you a virtual moment because it's a virtual. We cannot give you an in-face moment. So
thank you
on
so
behalf
much.
of the whole Para 21 teams, I would like to thank you again for accepting our invitation and enlightening us with your informative talk. So
thank you so much. Thanks.
Now we move to the second talk of the session. So without taking much of your time, permit us to introduce our second speaker, Professor Singh. So Professor Singh obtained his MTech and PhD in electrical engineering from IIT Kanpur in 1989 and 95 respectively. Presently, he is a professor at Department of Electrical Engineering, IIT Kanpur. Before joining IIT Kanpur, Prof. Singh was working with UP State Electricity Board as an assistant engineer from 1988 to 1996 and with IIT Roorkee as an assistant professor from 96 to 2000. And then with the Asian Institute of Technology, Bangkok, as an assistant professor from 2002 to 2002. He was also the Vice Chancellor of Madan Mohan Malviya University of Technology, Gorakhpur during the 2017 to July 2020. Professor Singh received several awards, including the Young Engineer Award in year 2000 from Indian National Academy of Engineers. Then Khosla Research Award from IIT Roorkee, Young Engineer Award from CBIP New Delhi in 1996. Professor Singh is also recipient of Humboldt Fellowship of Germany, Otto Monstad Fellowship of Denmark, and he became the first Asian to receive 2013 IEEE Educational Activity Board Meritorious Achievement Award in Continuing Education. Professor Singh is appointed as IEEE Distinguished Lecturer for Power and Energy Society from 2019 and Industry Application Society from 2019 to 2021. His research interests include power system restructuring, facts, power system optimization and control, security analysis, wind power, etc. Presently, Professor Singh is the immediate past chairman of IEEE India Council. Professor Singh is also the fellow of IEEE USA, IIT UK, National Academy of Engineers, IE India, and IET. It's a pleasure that he has accepted our invitation and spared some time from his busy schedule to enlighten us by his knowledgeable words. So on the behalf of whole Para Para 21 team, I would like to welcome him. So now I request Professor Singh to deliver his talk on digital energy transformation. Over to you, sir.
Oh, sorry. Yeah, I can also share my video.
Yes, sir, now you're audible.
Yeah. Yeah. So this talk will be thought-provoking. I'll be not giving any example. I'll be not giving any results, nothing. Just think where we are going from where. And that's why the topic I have chosen is the digital energy transformation. No doubt you can say this is I think the third shift, because first it was on the first day, then it was on second day. Now finally, anyhow, I could make it on third day because both day I was out of the city campus. So I could not make, but anyway, I'm going to talk about the digital energy transformation. No doubt we are talking much about the intelligent grid, smart grid. Now, what is going to happen in the future? If you're writing all the time smart, people are slightly fed up. And they're saying, what smart we are going to add? Whether our old grid or right now grid is not smart. So what parameters, what adjectives, what are new things and technology you are putting so that we are transforming our whole system in a very better way? And that's why this topic I have chosen. That's why I'll be starting with the certain, even though I'll be giving the glimpse of our country as well, where we are at this moment, as you know, about the power generation, etc. Then I'll be talking about the future grid, then what are the smart grid, why we are talking about all these things. Then I'll be talking what is the digitally we are going to use all these things, the digital transformation. And then at the end, I'll be talking about the what are the challenges, what are the things we have to look after. And those challenges, no doubt we are having certain sort of solutions. And I always, always we search, being a academician researcher, always we search for the best solutions. So it is keep on even though improving our own methodology. So from very beginning, you can say, keep on improving the technology, keep on improving the methods, approaches, that basically we are moving towards the digital energy transformation. So to start here, as you know, on the 31st August of this month, we are having approximately total generation of 386 gigawatt. Out of this, you can see the percentage where we say thermal basically including coal, lignite, gas and oil, because they are working on the thermal based technology if they are there. So the total is a 60%. Earlier it was 70%, more than 75% it was there. But now this percentage increasing because the renewable energy sources we are keep on adding, and that you can see it is a 98 gigawatt. And this 98 gigawatt which I'm talking, it is a grid connected. Thus, we are also having the renewable energy sources, those are not grid connected. And that is also having maybe the more than 1.3 or 4 gigawatt. So if you add together, now we have across, this is 100 gigawatt in the renewable energy sources. In this renewable energy sources, I'll come. It is, we are having, as all we know, we are having, even though hydro I have taken separately, this hydro we are talking about the large hydro. In the renewable here, we are talking the small hydro also. So this is also renewable, and you can say this is a constituting 12%. This addition is very slow because the creation of dams require a lot of fund and also a lot of agitations due to the displacement of the people, animals, and other things. So that is also it's not growing as that is required because this is also renewable, but there are many issues are there. Nuclear, as you know, it is for many years we are sticking around this. Earlier it was 4,800, now we are having 6,700. It was expected at one time when we had the 123 agreement with the US that this nuclear power will go up to 20 gigawatt. And now you can say we have not reached, because that is also, the people don't want this nuclear power, because we know we have very bad time when the Chernobyl case, as you know, here also it has in Japan also. So even the people are afraid, even though in India also, South India, there people are agitating that they don't want the nuclear power, because although it is near to the sea and the jungles, but still, if there will be any casualty, anything that is not desirable. So that given the growth is also, you can say it is around 1.8 for many, many years, and it will be continuing. It will be continuing around this. So yeah, another, you can say the sector-wise. Just before the 70s, when the NTPC was not, it was the state-owned. Because it was, although the energy is on our constitution, it's a concurrent matter, it's both state and central matters, it is related, but it was completely state sectors were there. And you know, it was known as the electricity boards were created by the act of the parliament, and the boards were operating. When government thought, and there was a lot of monopoly of the state governments were there, a lot of agitations, a lot of other things were there. Then NTPC was created, and it was in the central sector. Then most of the big projects were going to the central sector because the state electricity boards were not having money to go for. They were having almost sick due to the various reasons. I don't want to talk about that, but there were both technical and non-technical reasons. They were sick, and still right now also they are not even coming up in a very great way due to the various political and other reasons. So the central government started very rapid. That time private were not there. In 90s onwards, we started going for the PPAs, power purchase agreement. And then the private started coming in this, and that was basically sold based on certain agreements. It was also not in our country, you know, that is a very difficult, as you know, they are not project in the Maharashtra. That project was completely shut down because one government has signed agreement, other governments always reopen the case. And finally, there's nothing is happening, even though Iran was completely gone from whole world. So, but later, you know, the many like Reliance Power, JP Power, Adani Powers, many private powers also there came. And now you can see how the fast it is growing. Because the government priority is changing, as we all know. We don't have the money. Government want that they should be invested. Huge investment is coming in this picture. So that you can say the private is increasing very rapidly. The central government is almost standing still now, and the state government is also now trying to having some sort of, there's a way, and you can say now the 50% is in the private hand. And that's basically you can just say. So it started with the state, then the central was having more share. It was 50% share at one time, I can tell you. Right now also it was 50%, you will see that there's no private. And now we are basically relying on the private powers. And that's why this is booming for the competitive electricity market also, because the private investors are there, they want to make money, they want to sell, and the competition is very huge, and then the price is also going down. So that is basically the scenario of, I can say you, that is in our country. But you will see that's a renewable energy power, and this is a mission of all across the globe that we should go for the green power. And the green means that is a concern of environment, huge abandonment available in the nature because other fossil fuels are depleting. All the things are basically contributed, and the governments are having a lot of praise of each government, not only India. Each government is trying to have as much as extraction of power from the renewable energy sources. So you can say wind, it is a 40%. We are not having the very wind in our country, but this wind is older than solar. And the many like European country, you will find the wind is having large percentage. And the solar in our country, as we know, we are having huge solar in our country. That is a good one. And based on that, this is increasing. Each month, we are adding several megawatts in the solar. So it is keep on this data is very dynamic. Wind is not very dynamic because wind is almost saturated. We have, you know, only the coastal area where the wind is available, where we can have the techno-economic analysis. Suppose you are, I want to put a turbine in IIT Kanpur. How many times the wind speed is there which can generate the power? So the cost will be very high. We cannot recover even the cost of the wind turbine as well. So that is not effective. So it is only you can say the coastal area where we are having like Maharashtra, Kerala, Tamil Nadu, or maybe the Gujarat and the Rajasthan. That is basically having the windy area where we can have solar everywhere, all across the India, and that's why it is keep on increasing. So hydro, as you know, always it is going the hilly area where you are having small hydro. I'm talking, it is less than 10 megawatts capacity. It's also very less. Biogas and cogeneration where the mills and where the sugar canes and even the waste to power also. So that is also contributing some amount of energy. So you can say 99, it is there, it is on that day. And the total here, even though those are the grid connected, this off grid connected is just 1.5 gigawatt we are having. In which solar is maximum. As you know, the solar is remotely placed. We are putting the solar power so that the people can be energized, that they can get power if the grid is not available, especially in the hilly area also. Wherever you can say remotely placed area, they are. So this is the whole scenario. That's where we are reaching. When we become independent, it was approximately 1500. 1500 only we had the power, megawatt approximately. And now you can say this, we are talking about the gigawatt. So it was 1.5 gigawatt to now we are having the 338 gigawatts. How many times we have increased in 25 years? But what are the recent constraints? No doubt we are good. We are now in the term of power generation, but still we face there is a shortage of power. All the time we face that shortage of power. Now, what is the total requirement of the country? I want to tell you, it is not known. Why? Because we have not met any time to the load. We are giving the restricted demand. All the state electricity corporations, they are central government, whatever they are there, they are just saying that is whatever the peaking they are showing, it is a restricted demand, because we are not giving 24-hour supply to all the end users. It is limited. Maybe it is 18 hours, 24 hours, 22 hours, and so on and so forth. So based on that, the peaking which we are having, that we say, this is my peaking, but still we are going to manually set based on that criteria, and load setting are done in the peak hours sometimes. So the demand is increasing in the very. This Muhammad Sarik, he can. I can remove him. Yeah. So it is, as you know, that we require the power, and this keep on increasing. The life comfort is increasing. So the demand is increasing. And once the demand is increasing, we have to increase the generation. So that is not only sufficient. If you are increasing generation, you require the transmission network. So this whole the limited expansion of the transmission network as compared to the generation addition, because the load is increasing, we know always load and generation should be balanced. So we require some interface, and that is a transmission and the distribution system that will be interface if your generators are far off from your load centers. So the most of the generation in the T&D system, even though all this capacity and installed capacity, which I said and I showed, many of them are having the derated capacity, or they have expired their life. Why? Because thermal power stations, we say they should not be more than 30 years, 25 to 30 years, depending upon which type of the technology you are using. And now we are even many thermal power stations, we are running for more than 35, 40 years. So that there's even the predictability. When they'll be on, when they'll be off, it is not very sure. And that's basically another concern. So it is our transmission system, many 400 kV transmission lines designed 30, 35 years before. So there are also conductors are brittle, there's maintenance, and many even the outages may occur. So this, and we also require the expansion. So we require all this like generation, transmission, and the distribution systems in the addition. So those are the concerns. Also, increase the transmission and distribution losses. The transmission system, basically, we have made in such a way that it's not very lossy, because we are normally following the standards of these losses approximately, as we have done the load flow of all UP grid, we found it is not more than 3.5 or 4% of this. But the distribution loss, which should be 7 to 8%, not more than that, but that is technically it can be, but the total, if you'll see, it is approximately, we are saying there's many states are having more than 25% losses. So they are including the AT&C losses. Normally we say aggregated transmission and commercial loss. So this commercial loss means you are not able to collect the money, or maybe not metered properly. So those are basically the losses are also there. So that is a loss is increasing. Once you keep on increasing the generation demand, because you are not recovering to board, your AT&C losses are increasing. Lack of the dynamic data, many of the transformers are burning. Many a times, as you know, people say, oh, this transformer in the distribution sector is very common, not in transmission system, because transmission system always is designed, we know what is its capacity, and always we are having the margin. But in the distribution system, what happens? We keep on connecting, we are connecting 1 kilowatt, people are taking 5 kilowatt loads. So your calculation based on the transformer, which you are putting at any place, it's okay. But that is many, even the people are taking loads without unaccounted for, and the transformers are heated up, and they are the burning, are also its maintenance, and many other issues are also there. I'm not going that is non-technical issue, but the technically also we are not having the data, and we don't know what is the condition. Sometimes health monitoring and the control, those are not in our hand. And that if these data are there, then we can very easily know that's what is the life of transformer, what is the life of transmission line. So that is also lacking data. And the increased concern toward the vulnerability and the resiliency of the system under the natural and man-made disaster. So we are having always, there is a chance and the pro, that's a lot of even the vulnerable system, because for loading is very critical. We are loading our in a peak hours very close to that. Even though small disturbances or 1 or 2 lines are tripped together or one generator is gone, very difficult to manage the grid. And that's always there. So that's why our operators are very alert all the time. And that is happening. The growing environmental concern, we all know the global warming. So we cannot add more hydrogen. We cannot generate more power from the fossil and other fuels as well. Power quality, already the previous speaker was also talking about the power quality is another concern because we are keep on adding the power electronics based devices. These devices are very good for improving the power system performance. It is basically meant for many applications for the increasing the legibility, increasing the security, increasing the reliability of the system. Many things, power factor corrections. That is very in controlling the voltage frequency. Many things we are doing, but at the same time they are generating a lot of power quality issues, and they are most affected also. So it is a cyclic phenomenon. They are used for something and they are generating something and they are affected much. So that is then limited customer focus and their participation in the energy management. Why this limited? Right now, the customer focus has increased awareness better compared to the last. Suppose you are in the village and the supply has gone and call to your substation. Nobody will attend your phone call even. So the customer focus in it, you will see their mobile. If it is mobile is not working, some problem, then call 123 and then you will see that the response will come. So that's specifically customer focus there, because they know that if you are not responding properly, next day they will change the SIM. At the same time, they will go to the and change the SIM. But in electricity, so whatever happening, the power which is coming to you, you cannot change your supplier. So government is trying at the higher end. Now it is possible with the electricity market. That's you can change your supplier, you can change the power, but again in between if the transmission system is out, you cannot do this. So the power can be traded from other states as well. It is allowed. In our UP it is not permitted, but in the Gujarat and many other countries that states that you can buy power from other generating stations, that is possible. So the customer focus must be also given in this similar business, and the demand is keep on increasing. Those are the concerns. So our present power system is heavily relying on the fossil. Already I showed the data also, I showed the concerns, and the generation follows the load, which I want to tell you. Why I'm saying the generation follows load? Because the load is in your hand, and the generation in the generation companies or maybe your corporations, wherever you can say that it's there. But so what happens once you are going to turn on your load, you never ask to the utility, oh, I'm going to turn on my Tulu pump, I'm going to start my agriculture pump or so on and so forth, or switch event. So once your generation load is increased or decreased, the generation must follow, as we all know that, you know, the AGC, load frequency control, all we know very well. So it is we follow that should match your load, and generation should be matched, including the losses, of course. Losses in concerned as taken as a load. So that should be balanced, otherwise frequency will deviate. And the frequency, you know, it will cause the stability problem, many other problems. So we try to have a very narrow band of variation of the frequency. So that's we are doing then, and the limited ICTs. All our transmission networks from many years, it was having the communication system, right? Whether it's a PLC or it is a microwave, many type of communication, even the landline also we were using. So it was using, but the limited. But our future power system will be basically the more renewable energy sources, and that's we are saying we have to go for green power. If you are using clean coal, you should clean it. The washeries are now put out. We are designing the boiler in a very better way so that emission level can be reduced. So many new technologies are coming so that you can reduce the NOx and sulfur gases. You can reduce the carbon dioxide gases. So the cleaning of the coal is also done, and the nuclear power are basically the future that you can think of. Now another is happening. Now you can say load follows generation. It's the reverse of the previous, which is the slide. You can say generation follows. Why it is said that? Because this is basically the meaning of having the competitive power market. For example, if the price is keep on changing, price at this moment is 10 rupees, and maybe some of the appliances you can turn off and you can shift when the price is low. So you are looking at generation, because more generation, price is less generation, price is less. It's just demand and supply. So that is now going to happen, and it's happening across the globe, in India also, but we are not affected because our corporations are doing on behalf of us. But in the many country across the globe, they can see the variation. In our country, the 15-minute price is changing. So that is basically now it is going to change with the competitive electricity market. And we are going to use more and more This is the ICTs, information communication technologies, smart meters, and the digital technologies. Those are going to penetrate much and more. And therefore, we are saying we are moving from the conventional system, intelligent system. Now we are moving towards the smart grid. So the technological changes in the electricity sectors, because it is not that it is we are idle. No doubt many things are saturated. For example, we are having three phase. It was almost 200 years. Yes. Yeah, approximately not 200, something 150 years or so. The three-phase system is only there. We in the voltage levels already, you can say now we are keep on increasing, but it is also limited. So that's you can say, but what are the things we are, even the principle of induction machine, principle of the synchronous machine, transformer, this is long back, no change. So what are the changes? Changes you can say, that is the technological changes, which can say the new materials. And due to the new materials, the like polymers, composite, nano, superconducting materials, so we can have the reduction in the insulator size. Machine size is also low for the same capacity I'm talking. So what happened if the size you are keeping same, the power you can handling capacity you can increase. So earlier, once we were having like 5 megawatt units in the very beginning, when we become independent, then we added even though 50 megawatt capacity, then the 100 megawatt came, 100 and 110 megawatt, then 200 and 210 megawatt of a single alternator. Then later we added 500. Then we said, oh, it is a super thermal power stations where the 500 megawatt power generators, single unit was there. So there may be many units in one power plant. It's not one. So one alternator which was giving 500 megawatt. Now we are talking this one alternator is giving approximately this 1,000 or maybe the 1,500 megawatts capacity. How come? The technology is the same. Induction machine principle has not changed, but we have changed the cooling facility. We have changed the insulation materials in that, so that many technologies are basically given so that we can increase the voltage level of the terminal, because the power, as you know, current we have to minimize for the loss minimization, I square R, you know, for making I less, voltage must be increased. The terminal of the alternators are also increased. So these things, the insulator, the 400 kV insulator, disc insulator, you cannot carry on your shoulder. But now with the this polymer, another thing, now 765 string that you can hold on, you can solder it and you can take from one place to another place. Why this the material? So the materials are playing a very vital role in the various capacity, which I said. And of course, this everybody knows this alternate and renewable energy sources. They are basically, we have to tap this power. This is abundant in the nature. This is easily available, is almost cost-free, and also it is very available near to your load centers. And those things are also, that is a very important. So it is improving the energy security, energy sustainability, that is a part is coming. Another, the new technological and devices, you can say the power electronics. Oh, that has a change. The converters, no doubt the converters from very beginning when HVDC basically started and we started using, but now we are talking the various type of the smart converters and all this. Converter means it can be rectifier or inverter, so that will be there. Flexible AC transmission system, power quality conditioners, many devices are now the STATCOM, SVC, TCSC, all these things are used to improve our system. So we are very optimally operating our grid, our system, using these devices so that we can, total cost of operation can be minimized. Another technological advancements, we are having digital signal processing techniques, especially used for the various protection schemes. They are used for various analysis like power quality analysis, etc. that can be done. Sensors, smart meters. So these are basically used many applications. So that's using the sensors. Now we are talking about the smart homes. So many things are happening in terms of these digital as well. Intelligent control using AI and machine learning techniques, and the ICTs including IoT, machine learning, blockchain, all the things are now going to come in our electrical grid. So the core electrical is the same, the principles are same, but the other areas of research now coming into the picture, and that is, like solar. Even the VLSI people are also talking. So they are basically designing the solar panels and their solar, all the connections. And finally, we are using the grid. The control is the power electronics. And finally, we are taking the grid and we are talking about all the security and the inertia, many things and control aspects we are adding. So, so maintaining whole system where the lot of things which is a very intermittent on nature, like the renewable energy sources which I'm talking, wind and solar, they are not deterministic because they depend upon nature. And prediction is a very one of the challenge. No doubt we are doing the prediction, but if you look ahead hours, prediction, if you are predicting at this moment and maybe 1 or 2 hours ahead, this is very accurate. But suppose you want to do for the 24 hours ahead or many hours, then the error will go more. So in that way, it is a very much, it's a variable. And operating the grid, we require the new technologies and the wide area measurement system where the phasor measurement units are in place. Earlier, the RTUs were used. And the SCADA for the transmission system and the generation, it was there. Now we are also talking about the distribution, demand side distribution automation, where we are going to have the SCADA for the distribution system also. So that sitting in one room, you can all see on analysis, all the monitoring and control you can do there. That is also in the place. So the maintaining the quality of supply and IT-enabled services in the distribution sector, and that's why we are talking about the power quality. We can achieve the smart grid, having the communication and other thing using, and also we can operate the microgrids, where basically having the weak AC interconnections or maybe the small, where we are having more and more renewable energy sources locally we can operate, and then when power is required, you can get from grid. So these are the changes. Another is the market, already I talked. So it is basically also happening. And in our country also, we are having the two exchanges as we are loan. So that basically, it is changing in the market side also. So we have to manage our congestion. We have managed our many, even the operational issues, because if there's a sudden outage, and always we have to provide our end user with the cheap electricity or lower electricity so that they can be benefited from this electricity market. So the customer value that will be giving cross-border trading now has started. We are basically having the trading with the Bangladesh, Nepal, and Bhutan. We are having the connections very well. And it is basically the price based. It is not cost based, because right now the governments are setting the price. If it is a market, then it is set by you. Because once you go in the any vegetable market, any market, it is decided by you and the supplier, with availability, demand and supply. So that basically is happening across whole. This is in our electrical sector. So taking the advantage of new development, we are making our future grid more smarter grid. And already I talked about what we are doing, that you can say that we are having the very wide area monitoring and control at the transmission system. That is, we are very clearly monitoring. We are also monitoring with the help of the SCADA, another in the distribution sector. That is monitoring and controls are that basically are being done. And then we require the coordinated energy management. It is not only electrical management. It is the energy, means energy can be your transport energy, chemical energy, gas energy, all the energy that's where they are using. That's why we are talking about the electric vehicles. That's if you can reduce that, even the fossil fuel cells, those are used in your electric your vehicles, they can be replaced by electric vehicles. So that complete coordination is there. And then we have to go for the full integration of the distributed generations along with the large power generations together. So that is happening. And we have to tap the small also. I do remember when I was in the State Electricity Board, 20, 25 years before. At that time, we were not allowing in the study. I was also part in that study. Even though this like sugarcane factories, they were generating 5 megawatt power. We said that if they will keep on injecting and taking all the time, the grid will disturb and fail. And now you can say we are adding 5 kilowatt also to the grid, because the technology has changed. We are having a very fast controllers now. They are taking care of everything. So the power electronics at that time, I'm talking about the 80s when we were doing 89, 88s. So that now it is changed. So we have to tap the power wherever it is available. We are going for the green power, secure and reliable that is there. We have to give the customer value, I said, because we have to listen there. The customer should have the choice so that I can choose my supplier. I'm not saying you should have the many wire at your home, but the same wire can be used, but the supplier can be different. It happens. It is a feasible. For example, you are using your mobile, you are having the 2 or 3 SIMs in your mobile, 2 SIMs. So it is the communication signal that is which is provided by the, like suppose you are calling to US. No, this is small, they are not having satellites. Satellites is used. Similarly, the wire can be even higher, the open access, etc. can be provided. Another, we should also have the harmonize the legal framework. That basically allows the cross-border, and that is there. Of course, that is one concern, but we can have the neighbor countries. So we are already having our neighboring countries, those are connected by land, not Sri Lanka, not Maldives, and of course not Pakistan. So these things are, we are having, as already said, the Bangladesh, Nepal, and Bhutan, we are having all this connection. So from smart grid, now we were using the ICTs, information and communication technologies, and IoTs. But now in the digital energy transformer, there is a three powerful technologies which are trying to force us to go for the digital energy. No doubt the energy will be the sinusoids, as we know, but we talk about the digital in terms of emergence of the technology of the digital technologies, which is the Internet of Things, artificial intelligence, ML, machine learning, computing. That's a varieties of computing now it is available that you can compute anywhere and you can give this information anywhere. No need to have the centralized computation. So it is a cloud computing, and a lot of people are talking about the quantum computing and so on and so forth. Blockchain is going to be trading that they're going to use in terms of peer-to-peer trading and other things are happening. So that is basically coming the digital way. Another, the arrival of the increasing affordable distributed power. And that is a technology which is a better operational control now. So the distributed power is another technology, and the decarbonization, the using the renewable energy sources and having the high energy options like low carbon technologies are in the play. So there is a 3D, which is basically trying, and which is if we are going to use massively these 3D technologies, that will be known as the energy transformation, digital energy. Because the digitization, we know we can use the additional intelligent control. We can have internet-enabled software to optimize the plant and the grids, and the decentralized control that we can have the small scale generation through the TNDs, and the decarbonation, of course, as you know, the rapid deployment of these technology, wind and solar already we are doing, and we have to go for a long way, and massively we are adding in our system. So this is my last slide. So to have the challenges, there's no doubt once it is going to have in the digital energy transformation. Leah. So it is increasing the operational complexity, and the increasing operational complexity, you know, each generation, each load, they are behaving in their own way, and so the complexity is increasing. So we require the technologies, and already we are having the technology to handle properly. You can say the wind is the highest in the Tamil Nadu, but highest load setting in the Tamil Nadu, because the wind is just in the 15 minutes, maybe zero. And maybe there is a 7,000, 10,000 deficit of the power. Thermal power station cannot ramp so quickly, even though those are hard roll, it is, they are running that you can increase, but new you cannot start at the same time. So the many things, the complexity is increasing, and it is basically business oriented. Now earlier the electricity was the social term, and that's why the state government were trying free electricity to agriculture, free electricity. Now you can say the many campaign of politicians, the free power to all, or maybe the reducing or waiving up all these things, and the companies, those are coming, they also extract the money from the market. So it is a very complex, the business oriented. Earlier it was social, now it is those are coming in the market, they want to take profit and money from it. So who is sufferer? Again, the individual. So that is and it has a huge data. If you start trading, every second the power should be managed properly and recorded. Every minute we are just having this, depending on your meter capacity, what is the data rate. So you are having huge data. What are you going to do with this data? Then the data handling, data analytics. From those data, you can do a lot of even the better operation of the system. So that data handling, you know, the Google is having the smart grid in their office. You know, the Google, everybody is having Gmail, I'm sure. And you can say how that fast email, even though our system, those are having local servers, etc. Just see their Gmail mails are how slow, but the Gmail you can say you can on anywhere and it's giving very best results. So they are having. So if you are going for all these things, you are just working in the office and controlling your home appliances, then cyber and physical system. We are computers. Once you are taking the data and controlling, then it is based on the internet. And once you're on the internet, then the cyber and this one of the concern. That's why it is cyber physical systems we are having. It is very prone. People can even though tamper your meters, tamper your control actions and other thing, and that may create the grid collapse and other thing. So it is a tampering one here, one data, one meter, or whatever you can say. It is not only basically creating problem at local one, it's giving a global problem. Whole grid may fail. And that is a very challenging. Because if you're having something hacked your, like virus has hacked your computer, only your system is gone, not others. But here, if you're doing one, it is going for a whole affecting. So that is the cost affecting ICT which we require. Communications are still mature and still going in that way. We have to say which technology we have to use. Requirement of forecasting, already forecasting, once you're using the renewable sources, the fast forecasting and accurate forecasting are required. Demand response, now we change the prices, people should shift their demand here and there, and that may be taken in that one. And we can have some sort of market structure where that can be fit in. If you're having a very big market where small customers may not be fitting. So you can have even the local level, even the distribution level market also. So aggregator can have another market, global level, we can have another market, various time frame of the market. So all these things are basically now re-looked into the whole system in this new digital technologies. And that's the fast analytics tool, integration, how to integrate, suppose 5 megawatt, 5 kilowatt, you are going to connect 132 or you are going to connect 0.4. So all the things are basically grid codes. If there's a grid instrument, how they behave. That's why the grid codes are there for interconnection of renewable energy sources, their controllability, and many, many other issues are also. The low inertia, as we know, these are the problems of the renewable energy sources. Once we are integrating more and more, then how to tackle this virtual inertia, or we can say control inertia, or you can have some physical inertia like a rotating mass. We can put it the induction machine, we can flywheels, we can put the power quality, already power electronics once we are adding. So it is. So the many, many more are combination of all these things are happening all around this. So these are the challenges, no doubt. We are having the solutions as well, but always we have to have the better solutions, and that's why we are doing all R&D. So with this, I'll say thank you very much. I think I crossed only 9 minutes, so it is okay.
Thank you, sir. Myself, Achilles. Thank you, sir, for enlightening us with your perspicuous speech. I believe everyone has got a new perspective of digital energy transformation from this amazing presentation. Sir, we have some questions that were sent to the chat box. Please allow me to read it.
Yeah.
So the first question is from Avinash, and he's asking, are we moving towards hybrid AC and DC power in distribution to household? So if it is there, then what are the real challenges?
Basically, no doubt, always it is said if you are going for the small usage or small pattern, so DC is also equally well. And since we are having the many level of converters and our end users are going to be the DC, you can say in a house, earlier you are having the light and fan. And with the help of this now, the computers, mobile charger, UPS, all this, and now the DC power we are taking. Even though now fan also we are having the BLDC fan. Lighting, it is almost, you can say LED and other things, DC power is required. So now our distribution system loads are going to be the DC. Once it is DC, then people say, why we are going for AC to DC? So once you are going to AC to DC, you require a converter. And then from there, you are distributing it. But if you are going for the new house or design, you can now, people are talking about the pico grid, where the house is also a grid if you are taking, where we can have only one converter at the room, and then we can have the DC wiring. And then we can have the different voltage level. For example, if the charger of my mobile is 5 volt, if the charger of my battery, UPS is the 12 volt, and whatever you can say, so then we can have those voltage lines, and then we can connect and we can do it. That is possible. Only the problem as you face, if there will be any fault, then the switching operation that you require a controller, good controller for that, otherwise it will burn. So the DC, because as you know, for the switches, if the overcurrent relay is there, it's the high current is going to be tripping it. But in the going for the larger and other things, so the control aspect is one of the looked into. But in the future, maybe we can, of course, the AC is there. So, but if you're having AC DC together, now it is see how many converters you are having, what are the conversion losses are there. Based on that, you can analyze. And then even the future people are trying to say, we can go for the DC in the houses. Because now your small appliances, like even though you are having the inverter based your washing machines, fridges, they are now having the power electronics, etc. But you have to see what is your usage. If usage is very high, then it is better to go for AC and then convert at that point only. So that is, again, it is a very techno-economic analysis depending on the demand, supply, usage from where power, what is the level of power requirement in your house, and which type of appliances you are using. So it is possible. AC and DC, maybe in the future it can be.
Okay. Thank you, sir. Another question is from Vivek Kapil. He is asking, elaborate the use of blockchain technologies in the power system.
You see, this blockchain is basically is very well used in the peer-to-peer trading, because you are the 1 and 2 persons are trading maybe the bilateral transactions, are having certain sort of transactions they are doing, a multi-level transactions, where this you don't want that currency should go, and it should be also very hidden, and this currency and this trading could be basically the safe and secure. So the already the, the Bitcoin is already people were doing some sort of the trading, but not for the energy. So similarly, using the blockchain, the methodologies that is used in the electrical trading, and people are trying to use this one. And although it is a very nascent stage, still, but the people are trying to work hard, and a lot of now papers are coming up in the, you can see in the transactions that are based on this blockchain methods for the our electricity market. It's a very well application here is electricity market, where you can have it submit trading.
Okay. Thank you, sir. Actually, we have some time restrictions, so we'll take just one more question. This question is from Deepak Porwal. He is asking how reactive power and voltage profile challenges are coming in the transmission and distribution system with the integration of renewables.
Yeah, due to the renewable, what is happening, because the renewable, once we are connecting, it is mostly the renewables are connected by the power electronic interface. Because either it is a for wind, you are having either full converter or half, 1/3 converter, as you know, the DFIG or the synchronous machine, where the permanent is there. So once you are connecting, and these powers are changing. Once the power is changing, the voltage rise and other things are concerned. But at the same time, what we are going to do with the help of these power electronics devices, we can control. We can use something sub voltage control very easily. But the frequency control is very, very difficult, because it's related to active power. And once active power is not given by these renewable energy sources, then we have to meet from our renewable energy source from the conventional sources. That's why I said in the Tamil Nadu, more wind, more but more blackout. Because if I should be ready, suppose there is a 10,000 deficit, suddenly 10,000 megawatt is lost by generation. Then I have load. Option is to go for the load setting, or you have to increase the generation. Once you are increasing generation from where? Thermal power station, those are connected, and it has a maybe limited capacity to increase. It will increase few minutes. It can be having ramp rate properly. But suppose 10,000, you have required some new power plant to turn on, then it is a very, very difficult. That's why once you are going for more. Another is your frequency response. They are having the less inertia. So if your thermal power stations are off and only you are using the solar and the wind, your inertia of the system is there. So sudden change in the demand and supply, that will be changing the fluctuation. So we require the virtual inertia. Even though Denmark, there's a lot of flywheels are running to create the kinetic energy stored in this, or you can have another storage system. If you're having the other storage system, you can meet that energy certain requirement. So those things are there, then only otherwise there's a lot of variation in the voltage and frequency.
Thank you, sir. Thank you, sir, for answering all the questions. Dear participants, we have some restrictions on the time. So if you have any further questions, you can post us to our mail ID. We will forward it to the Professor Singh, and we'll get your query answered from him. So now uh, I would like to, on the behalf of Team PERA, I express my sincere gratitude to our speaker, Professor S.N. Singh, for delivering such an insightful lecture. We highly appreciate you for accepting our request and giving us the valuable time from your super busy schedule. The talk was highly informative. I firmly believe that this talk will be instrumental in future learning as well. The knowledge participants will carry home from this session will help them in their career too. As a symbol of gratitude, we request you to accept a virtual token of appreciation. Now move.
Thank you very much.
I hope you all are already aware about the ongoing voting process of IEEE and its society. It will close at 12 noon US Eastern Time on 1st October. If you have not voted yet in the IEEE election, you can still vote. Don't miss your chance to influence IEEE's future. To make your vote count, use the link given in the chat box and we will share it also via email. I love to take the opportunity to re-inform you that IEEE Governing Board has nominated Professor Srinivas Singh as PES Secretary Candidate for year 2022. He doesn't require any introduction. You all know him very well. However, kindly allow me to give a brief credentials of his candidature for IEEE Secretary. He started as a member of IEEE over 21 years ago. He has served IEEE as executive committee member at multiple levels, including UP section, India Council, Region 10, and PES society level. He is an IEEE Fellow and received various IEEE awards. He has been ranked fourth in top researcher in energy area by DST New Delhi and in the top 2% researcher in the energy area in the world by Stanford University ranking. He has really impactful plans to take the IEEE PES to new heights. He has pledged to develop more continuing education, reducing membership fees, and ensuring transparency in all the decision making and strengthening the local, sectional, and regional chapters. Here, it is my suggestion to go through the credentials of Professor Singh and other candidates also. Make your choice and do vote. I once again request you to do vote before it closes on 1st October at 12 noon US Eastern Time. Now, I would like to thank the participants for joining today's session. It is you who made this session successful. We would be waiting for you in the next session. It Professor Francisco will deliver his lecture and then at 6 p.m. the demonstration of RTDS hardware in loop will be there. Now, with the permission of Professor Singh, I would like to end this session. Have a good day.
Thank you. Thank you.
Thank you, sir.